Welcome to part 2 of the Dynaco SCA-80Q series. In part 1, I unboxed the never-opened 1978 kit, and I speculated that many of the old components would now be bad. If you missed that episode, you may want to go back and check it out. So I've now tested all of the kit's 43-year-old capacitors, resistors, transistors, and diodes, and in this episode, I'll share my findings. At the end, I'll also test the transformer. Before we start, though, I want you to take a guess about how many electrolytic capacitors you think are bad in our kit. Is it 10%? 50%? 100%? And how about the other capacitors? The resistors, the transistors, the diodes? How many of those do you think are bad? I guess we should start by defining what bad really means. In the case of resistors, that's easy. They're color-coded and they tell you exactly how far out of range they can test for resistance. And resistance is tested with an ohm meter. With diodes and transistors, it's pretty easy too. At this point, we just want to make sure that they're not open or shorted. And we can do that with a multimeter or semiconductor analyzer. We first test capacitors to see if they're out of tolerance with a capacitance meter. And with paper, mylar, ceramic, and silver mica caps, that's usually not a problem, as they often have their tolerance stamped right on them, either explicitly or with a code. Electrolytics are trickier though. Many circuits operate just fine with an electrolytic that's 50% higher than rated capacitance, and most often they're not even marked for tolerance at all. But most manufacturers claim their new electrolytics have a 20% tolerance, so for our purposes, any that test 20% or higher than rated capacitance will be considered bad. In addition to capacitance, we also need to test an electrolytic's loss and leakage. To measure loss, we use an ESR meter, which measures equivalent series resistance, or in other words, how much the capacitor resists passing an AC signal. There are generally accepted standards for how much ESR is acceptable, and a lookup table is often used as a reference. To measure leakage, we use a leakage tester, such as my tried and true antique Heathkit IT28. It adds DC current to a capacitor to see how much actually leaks or gets through. An ideal capacitor will pass no DC, which will be indicated by an open window on the Magic Eye display. And a closed window indicates the capacitor is leaking DC and needs to be replaced. And note that all types of capacitors can be tested for leakage, not just electrolytics. So now that we have some ground rules, one more chance to guess. How many capacitors, resistors, transistors, and diodes do you think tested bad in our old kit? Let's first look at the capacitors. As I expected, the typically reliable ceramic, silver mica, and mylar capacitors tested well, and 100% of the three types shown here tested perfectly. There was one ceramic disc capacitor that was out of tolerance, but 92% were fine. Overall, a solid showing. Electrolytic capacitors are more likely to age poorly, and predictably for me, 50% of the small electrolytics tested bad. Here's a 47 microfarad cap, for example, measuring 40% high at 68 microfarad. And this one is completely open. The three large electrolytics and the multi-section can completely fail the leakage test. Here I'm testing one of the 80-volt 5000 microfarad caps, and it didn't even pass at 50 volts. Here's the multi-section electrolytic. The section I'm testing here is supposed to be good up to 75 volts, but was leaking DC even at 50 volts. So an overall bad showing for the electrolytics, and that's why I'll be replacing all of them, even the ones that tested okay. That's because even those still aren't as good as modern equivalents. Compare this 470 microfarad cap from the kit, for example, that's coming in at 0.2 ohms ESR. That's good, but the replacement I'll use has only 0.08 ohms of ESR, so no contest. Okay, how about the resistors? Well, 100% of the carbon film, ceramic, and metal film resistors tested good. Impressive considering that these are gold band resistors with a strict 5% tolerance. These are excellent components and no replacements will be necessary. The carbon composition resistors, though, failed miserably. 50% tested bad. Here's a 4.7K carbon comp, for example, coming in at 5.5K. That's 17% high on a 5% tolerance component. So I won't be taking any chances with the carbon comp resistors, and even the ones that tested well will be replaced. I actually do have quite a few modern carbon comps in stock that I've had good luck with, so I may use those. Then again, carbon comps generally aren't considered as stable as carbon films, so I'm not sure. In the end, the decision will probably come down to what I have in stock, so stay tuned. Moving on to the semiconductors, all of the transistors and diodes included with the kit tested fine, so no replacements necessary there. Here's the lineup of all the capacitors and resistors that tested poorly. Is this less, more, or about what you expected? Let me know in the comments. Well, if you blew it with your guesses, here's another chance at redemption. Let's now test the power transformer. What do you think? Will it be bad or good? Let's find out. Before we install the transformer, let's give it a quick test to make sure it's operating okay. My test setup looks a little complicated, but it's actually pretty simple. First, note that the green and yellow wires coming from the transformer are from the center taps and they're not used in this amplifier, so I just have them wired down here and not connected to anything. There are 2 coils in the transformer that could be used as secondaries, but in this case they're using them as primaries. And those 2 coils are wired together in parallel to function as one. So here you can see there are 2 black wires, each connect to one end of the 2 coils. And here you see there's a purple and a purple-white wire which are connected, and these both connect to the other side of the 2 individual coils. And as I said, these are connected to operate as the primary, so they're connected directly here to the AC input, which I have connected to my current limiter, which is connected to my variac. On what's being used as the output of the transformer, there are just 2 wires which come out here, the 2 red wires. And with 120 volts going in, we're supposed to have 54 volts here. And to measure that output, I have my fluke set up here, and we'll read the AC voltage that's coming out of the transformer on the screen here. Let me flip the fluke into AC mode now. And on the input side, I've got my variac set up so we can slowly ramp up the voltage to about 120. And in between, I've got the current limiter just in case we wire something incorrectly, and this will give us a margin of safety. And note too that I have a voltage meter here on the output of the current limiter so we can actually monitor the voltage going into the transformer. Let's begin. The fluke is turned on. Let's turn the current limiter on now. If there are any problems or I wired this incorrectly, we're likely to see this bulb glow, indicating that there's a short. If the bulb does glow, we'll back off and check our connections. Now the variac, and let's slowly ramp up our voltage. You can see that with 52 volts going into the transformer, we're getting an output at about 17 volts. Let's ramp it up all the way. About 90, 100. Let's go to 120, just about there. And our voltage is, about 54.5. Yeah, that's absolutely perfect. This transformer is working just great. Okay, we can now finally start building the amplifier. Let's do that in the next episode. Stay tuned. To stay updated, please subscribe to my channel and click the bell to receive notifications when I release new videos. And if you like this video, please give it a thumbs up. I'll see you soon.